Okay, so more Buckingham PI Theorem, and this time we're going to look at trying to understand wall shear stress as a function of stream velocity, boundary layer thickness, density, local turbulence, and local pressure gradient, dpdx. Now, what is the physical setup for this problem? I don't even know. Yeah, it's just some example that I found, and it looked like a good one, and so let's get into it. So what we basically need to do is first look at the variables that are involved in this problem. So we've got our wall stress. So this is going to be, this has units that look like mass times length inverse time to the minus 2. And then there's velocity, local turbulence, which is LT inverse. Then there's our pressure gradient, and this one we saw from the other video has units of m L to the minus 2 T to the minus 2. And then let's see, so we've got our stream velocity, which we're calling U, so this will be LT inverse. And then there's the density rho, which is in units of mass times length to the minus 3. And then we've got our boundary layer thickness, which is just in terms of units of length. All right, so looking at all these things here, we have total number of variables is equal to 6. And if we look at the number of different quantities we have appearing on the right, there are 3 of them, ml and t. And so we expect to have 6 minus 3, so that's our n minus k, is 3 pi groups. And so the pi groups are going to be our dimensionless groups. So these okay, and so that means that according to the Buckingham PI Theorem, we expect that we can reformulate this, we can formulate whatever physical law relates tau and these other variables in terms of some expression where we have pi 1 is going to be some function of pi 2 and pi 3, where each one of these pi's, so pi, let's say pi j, is some combination of the variables given in the problem. Okay, and so the trick is how to go about figuring out what those suckers are. All right, so now what we need to do is pick some variables that we are going to call repeating variables. So by the way, you might notice this one is a little less ad hoc than the example I did before. The one I did before was fairly simple, so I could just kind of do it off the cuff. This one's a little bit more complicated, so we're going to get a bit more systematic about it. Okay, so we need some repeating variables. So I'm going to choose 3 variables that together will not form a pi group. And so I'll take these guys right here to be my repeating variables. And I'll build pi 1 and pi 2, pi 3 out of those. So let's see. So for the, actually, yeah, sorry. I misspoke. I will build pi 1 out of tau and some expression for my repeating variables. So here there will be, I'm going to have rho to some power, u to some power, delta to some power. And I know those are good. I'm using exponents, so a function of this form, because I want those dimensions to cancel out. Okay. And then I will do something similar for figuring out what pi 2 is in terms of velocity, and rho a ub delta c, and pi 3 for, who's my last variable? The pressure gradient. So the pressure gradient in terms of rho a ub and delta c. And I'm using terrible notation here because these for these equations right here, these are different a, b, and c. I'm going to solve for a, b, and c separately for each equation. So let's do that now for the first one. So from pi 1 being equal to tau times this business, what do we have? Well, so we know that on the left are dimensionless quantity, so we've got a 1 here. And then on the right, we've got, let's see, so tau comes in dimensions m, L inverse t to the minus 2. And then we're multiplying this by rho to the a, so that's m, L to the minus 3 to the a. And then by u, so that's LT inverse raised to the b, and then delta, which is in units of L, raised to the c. Okay, and so in case it's not totally apparent, what we actually have here is a system of linear equations with coefficients a, b, c to be determined. And so let's see what we've got for those right there. Well, what I need, maybe I'll rewrite this by multiplying the term for tau over to the other side, and then we can see how to equate the exponents. So this is going to be m to the minus 1 L t squared. And so now you can see how many rhos, u's, and deltas I need to figure this thing out. To make the sides match. So let's see. So if I look at the equation for m, the equation for m tells me that so there's only an m appearing right here. So I know that on the left side I have m to the minus 1, and on the right side I have m to the a. So that one tells me minus 1 is equal to a. If I look at the equation for the t's, then on the left side I have an exponent of 2, and on the right hand side, adding up all the exponents there, I just have an exponent of minus b. So then that tells me that b is minus 2. And if we look at the equation for L, then on the left hand side I have a 1, and on the right hand side I have minus 3a plus b plus c. So so earlier I mentioned we're getting a system of linear equations, and so maybe it's only at this point that actually becomes clear. So let's see. So we saw that a was minus 1, so this is 3 minus 2 plus c, and so I get c is 0. Yep. Okay. So so going back to the original equation that we had there, pi 1 is equal to tau, and then I've got rho to the what was a? Rho to the minus 1, and then u to the minus 2, and then delta to the 0. So in other words, it does not show up. So that's telling me that my my first quantity is given by this expression right here. So if I'm looking for tau, it's going to be actually, sorry, let me rephrase. So when I look back to my formula, I'm going to have tau over rho u squared on the left-hand side is equal to a function of, and then my pi 2 and pi 3 on the right-hand side. So now we need to find pi 2 and pi 3. Okay, so the pi 2 equation was velocity, and so let's solve this again for A, B, and C. So on the left-hand side here, we've got a dimensionless quantity, so there's a 1 there. And then on the right-hand side, let's see. So we've got the velocity, so that's length per time. And then we've got rho, so that is ml minus 3 to the a. And then we've got the u there, which comes in units of L over T. And then we've got our L to the C. Okay. So again, I've got an M equation of, let's see, well, there's no M appearing on the left-hand side. Oh, I forgot to cross multiply. So let's take TL inverse equal to this stuff here. Otherwise, it's just too easy to make a sign error. Okay, so that being said, okay, so let's look at M. So we know that A is going to have to equal 0 because there's 0 M's on the left-hand side. And then we look at the equation for T. And so on the left side we have 1, and on the right side we have minus B of them. So that tells you that B is minus 1. And then we've got the L's. So we've got on the left side minus 1, and on the right hand side we have let's see, well, that A is equal to 0, so I can forget about that part. So I've got B plus C of them, and I know that B is equal to minus 1. So apparently C is equal to 0 again. Oh, poor C. Never gets to have any fun. Okay, so then that tells us, so we've got that pi 2 is V times u to the minus 1. Yep. Okay. So V over u. Oh, that makes sense. That's definitely a dimensionless quantity because velocity divided by a velocity is going to give you something dimensionless. Okay, fine. Let's go on and look at the last one. So pi 3. So this is going to be for our pressure gradient. And so the pressure gradient is in terms now of where did I put that? Oh, there he is. M L to the minus 2 T to the minus 2, and we're multiplying it by our rho, which is ML minus 3, and our U, which is LT minus 1, and the radius. Okay. So the equation then is that L squared T squared M to the minus 1 should equal this expression over here. So that's going to give us an equation for M. So for m, we've got a -1 on the left and an a on the right. So a is -1. T is going to give us a 2 on the left and minus b on the right. So we have b is -2. And then for L, we have 2 on the left, and then we have -3a plus b plus c on the right, and back substituting gives us c equals 1. Okay, so pi 3 looks like pressure gradient, and then we've got a rho in the denominator because a is -1, and we've got a u squared in the denominator because b is -2, and then we've got a delta. Okay, so then the final conclusion from all of this is that if we go back and look at our expression for, so it was supposed to be pi 1 is a function of pi 2 and pi 3, and so that becomes pi 1 was our shear stress over rho u squared, and so this is going to be some function of velocity divided by turbulence, or vice versa, and then px delta over rho u squared. Okay, so long story short, we have taken an equation relating 6 variables. So we've got so the function would have been a function of 5 variables, and we've reduced it to a function of just 2 variables, these sort of conglomerate things. So anywhere in the formula for f, wherever v appears, it appears in this ratio with u here, and wherever delta appears, it appears with all these other terms in the same mess, so on and so forth. Anyways, so now we have a function of 2 variables, and it will allow us to give a law for this quantity right here, which is some crazy dimensionless thing, doesn't matter. Once you've figured out what that actual function is, then you can go ahead and do more stuff.